Welcome everyone to the quick seminar. Today we have Nicolas Delfosse, who is a senior researcher at Microsoft, and he's leading their efforts on quantum error correction and quantum computing. And today he's going to talk about improved quantum error correction using soft information. Please take it away.
Thank you for the invitation, and thank you everyone for joining. I'm happy to talk about this recent paper. It's a joint work with Chris Pattison, who was an intern in our group, and with Michael Beverland and Marcus Silva. And it's about closing the gap between what we do in most of the literature, in the quantum error correction literature, and what we observe in a lab when we run an experiment, when we run a measurement. There is a gap between the two models, between the model and the experiment, and we're going to try to close the gap and to use the extra information that is usually not used. This extra information is a soft information, and I'm very excited by this result because it's one of the places where we can still get a very significant improvement of the surface code that has been optimized for 15-20 years, and we will see that based on our numerical simulation, we can expect an improvement of multiple orders of magnitude in the performance. So first, as I was telling you, the motivation is the gap between theory and experiment, and I'm going to discuss the surface code. So we are going to consider this square grid of qubits, where each node is a qubit. Here we have a 5x5 grid of qubits, and we will run plaquette measurements. This is Kitaev's code. We'll run measurement on plaquettes. And based on these measurements, we are going to be able to detect errors. So a Z error, a Pauli Z error on a qubit, is going to translate into some non-trivial outcomes on incident plaquettes. Based on non-trivial outcome, we know that there was an error around there, and we will be able to correct it. That's the goal of quantum error correction. And what we observe in practice is slightly different. We expect plus or minus one outcome on the plaquette. This is what we use in theory. But in practice, the measurement outcome is very noisy. We have continuous noise. And what we expect is something closer to a real value. We're going to have a real value plus 93, plus 0.93. And what can we do with that? So the first thing is, how can we use this real value instead of a binary outcome? And the second thing is, can we benefit from it? Can we improve the performance of this error correction scheme using this real value and this extra information contained in this real value? Okay, so in this talk, I'm going to start by introducing the model. So we need to have a more precise model to go from binary outcome to real values, or to more general outcomes. I'm going to tell you how we describe a measurement. And then I'm going to discuss directly the applications. What is the performance that we obtain using this noise model? I can hear some noise. I don't know where it comes from.
Yeah, let me fix that.
Okay, thank you. I'm going to keep going in the meantime. Okay, so after our model, I'm going to directly describe the results.
Maybe a naive question, if I may.
Yes, of course.
So what is the drawback of like applying the naive strategy of just like applying a classifier in order to like categorize like whether binarize the measurement outcome? What do you lose?
So we are gonna apply a classifier somewhere. The question we're asking is, should we reject all what should be the output of our classifier? Should it be just a binary output, or should it be something more that gives us the likelihood in addition to the value plus or minus one? And I cannot tell you the drawback without spoiling the conclusion, but the conclusion is that this extra information allows us to improve the performance significantly.
Okay, so it's like kind of doing like a regression then, instead of just a classifier.
Yeah, it's in the end we are going to end up with exactly with machine learning questions like that, and maybe I can take back your question later when I show the numerical results.
Yes.
I want to start the other way around, because typically we start with binary output. So instead of telling me it's a drawback to go back to binary output, I'm gonna tell you there is an advantage in using all this information. But there is a gap in performance.
Great.
So my goal with the section 2 and 3 will be to tell you what is the improvement in performance. So the first 3 sections are designed to be as accessible as possible. If anything is not clear, please let me know. And the last section will be the more technical part, where I will tell you how we design this soft decoder and how do we exploit this soft information. But before, I will tell you about the results. So first, what is a measurement? Traditionally, in the error correction model, we have an outcome plus or minus 1. Here, we're going to do it in 2 steps. First, we have an ideal projection, which is going to project our single qubit state onto the state 0 or the state 1. And depending on the 2, we are going to sample an outcome from some distribution. It can be any distribution. And we have 2 of them, one that corresponds to the qubit 0 and one that corresponds to qubit 1. Projection 0, projection 1. So we have an ideal outcome, which is unknown. And from this ideal outcome, based on this ideal outcome, we sample from some distribution that give us a soft outcome. And we will assume that those 2 distributions are independent, and they are independent over different qubits or different time steps. And now, how do we get back the traditional hard outcome, plus or minus 1 or 0 or 1? We take our soft outcome, and based on the probability that we get this outcome when we sample from F0 or F1, we are going to associate a hard outcome. So for instance, if we get this soft outcome mu, which corresponds to this vertical line, it's more likely to come from F1 than F0. Therefore, I'm going to associate the hard outcome 1 with this soft outcome. And within this process, there can be a fault. We can imagine that we sample from F0, but we get a very rare outcome, like here. It has a non-zero probability, and we will assume that the hard outcome is 1. We will assume that the outcome was 1. It's a fault. It's a soft flip. Is that clear? So basically, the traditional model takes as an input the hard outcome, and here we are going to try to exploit this additional information, which is the knowledge of these 2 distributions. And given this hard outcome, we can run the standard hard decoders and run error correction, ignoring the soft outcome. But we should not do that. We should exploit this information. Okay. I'm going to go with some examples to clarify the model. The model we consider in our simulation is Gaussian noise, one-dimensional Gaussian noise, but it works in any dimension. So we consider an ideal outcome, 0 or 1, or plus 1 or minus 1. And based on this ideal outcome, we will sample from F0 or F1. So if we have an outcome 0, we will sample from this red distribution, a Gaussian centered in plus 1. And we will get a soft outcome, which is likely close to plus 1. If we get something like 0.83, for instance, the hard outcome is going to be mapped onto 0, which corresponds to the red distribution, because it's close to plus 1. It's a trivial outcome. A second example with a soft flip is when we start from a -1 ideal outcome, We sample from the blue distribution, and there is a small probability that we get something like 0.14, which is on the positive side, and which is going to be mapped on a trivial hard outcome because it's more likely to come from the red distribution. So there was a flip within the sampling of this Gaussian distribution. And now, excuse me. Now, what is the soft flip probability? The probability that we have a flip inside this model is given by the tail, the integral of the tail. So this tail must be small if we want a small flip probability. We will consider two regimes, one where we have a small variance for our Gaussians, and then the overlap is small, the soft flip probability is small, and another regime where we have a large variance, and then the soft probability is large. Okay, so if there is no question on the model, I'm going to move to our numerical result. I'm going to tell you what kind of performance we obtain by using this soft information.
So what does this model correspond to, right? Because you know, I guess if you implement this somewhere, then what do you measure that will give you a real valued outcome like that?
Yeah, so what is this real value? It's the output of the classifier. So we get a signal. What's happening is that we are going to integrate some signal over some period of time during a measurement, and based on this signal, we'll assign a likelihood that it comes from one of the two qubits, the excited state or the ground state, the qubit 0 or 1. So this number, this unique number that we use is the likelihood.
Okay. All right. Thanks.
And the model we consider, the reason why we consider the Gaussian is because it's the most simple. In practice, you can imagine any model. We also consider a second model that I'm gonna describe later, which is a bit more sophisticated and maybe more realistic. Maybe it's going to clarify what this soft output is. Okay, so now I'm going to discuss the surface code. Before describing the numerical results, I need to tell you how we measure those plaquettes, how we measure those, we implement these measurements inside a plaquette. And the circuit for our measurement is based on one ancilla qubit that we prepare in the plus state, 4 CNOTs, and a measurement. When we implement this circuit, if there is a Z error on one of the qubits, we can propagate it through the circuit, and it's going to propagate to the ancilla qubit and flip the outcome. What that means is that a Z error is going to be detected on the ancilla. This is what we were saying with an error detected on the neighboring plaquettes. Now we need to run this circuit. This is for X plaquette, for one type of plaquette, and we need to run the same circuit by replacing CZ by C0 by CZ on Z plaquettes, and we want to run them simultaneously. And it's a standard circuit that we can do that. We can do that in 4 steps. So we prepare our ancilla qubit on each of the plaquettes. This is for 3x3 surface code, but the same circuit applies for any size. And then we apply our 4 rounds of gates, CZ or CX, CZ or C0, depending on the plaquette. And in 4 rounds, we can apply them in an order that is satisfying. So we use this circuit. And what kind of noise do we put in this circuit? We consider 3 standard noise models. The first model that we will ignore later because it's too simple is perfect measurement model, where there is only noise on the data qubits. The ancilla is perfect, the measurement is perfect, the gates are perfect. But it's a bit too simple. If there is no noise in measurement, how can we have soft noise? So the second model is phenomenological. And in this noise model, we have noise on the data qubit and on the measurement outcome. In that case, we can add some soft noise. And the model is well defined. That's the first interesting model that we will consider. And the second model is everything is noisy. In that case, preparation, measurement, and also even a waiting qubit or a qubit that is subject to a CNOT gate will suffer from noise. And we will also simulate this model. Okay. Now, first model, phenomenological noise. So qubits and measurement are noisy. And we add the noise in the measurement is soft, is due to a Gaussian distribution. And what we want to know is how does the decoder perform? So we use a union fine decoder that I'm going to discuss later. We use a soft union fine decoder and a hard union fine decoder. So we use the same decoder basically, but it takes different inputs. The first one will take as an input the whole soft information, so this value 0.83, and the second one will take as an input only the hard value. So instead of 0.83, it's going to take +1. And the performance is very different. One way to measure the performance is to compute the threshold. So below this threshold, the performance gets better with the when the size of the system increases. So we see that the logical error rate goes down, and above the threshold, the logical error rate goes up, and we cannot use our codes. So this error threshold is the error rate that we can tolerate with this code. And it moves from 2.6% for the hard decoder to 3.6%. So we have a significant jump in the threshold and an even bigger jump below threshold. Okay. So now here we compared two decoders, the same decoder for hard and soft information. But we can do even better. We can compare the soft union fine decoder with the best possible hard decoder. And the threshold for this best hard decoder is known. It has been estimated by statistical physics argument. It's close to 2.9%. So we are 25% higher than the best possible hard decoder, which is very encouraging. Okay. Now I'm gonna refine a little bit this model. So we use a phenomenological noise model, and we said that the outcome is obtained by sampling from some distribution, from a pair of Gaussians. But it's possible that there is some noise before the measurement on the ancilla qubit, and this noise will introduce a hard flip. So here we will consider a different ratio of hard flip and soft flip. Basically, we are considering what is the contribution of the measurement apparatus to the noise. And we have two extreme regimes. One where the measurement is almost perfect and all the noise in the measurement outcome comes from the qubit that was flipped before, from hard flips. Or another regime where there is no hard flip. The qubit was perfect until the exact point where it is measured, and then there is some soft noise that is due to the measurement apparatus, due to the integration of the signal. So it corresponds to a very narrow Gaussian, which is actually just a discrete distribution with a single non-trivial value, or a large variance. And on the left side, when we have no soft flip and no soft information, the hard and the soft union fine decoder match, which is a good sign. We recover the previous results. And on the right side, we obtain the 3.6 threshold. In between, the threshold gets better when we get more and more soft information, when the ratio of soft flip and hard flip becomes larger. And the realistic regime is probably somewhere on the right side. It depends on your qubit, on your hardware, on a lot of things. But it seems that measurements are one of the main sources of noise. So we expect this kind of soft information to be relevant. Okay. Now I'm going to discuss the circuit model quickly before we move to a different application. So in the circuit model, we also obtain an improvement. We obtain an improvement, a small improvement in the case where the probability of an error during a measurement is the same as the gate error rate. Then we have a slight improvement in the threshold. And we also consider a model where measurements are 10 times more noisy than gates, which is also something we observe in some experiments. And then we have a more significant improvement, and below threshold, we obtain a performance improvement, which is a constant factor, but this constant seems to increase with the distance. So the larger your code, the better the improvement. And we get something like a factor 3 for the distance 19 surface code for the logical error rate. Okay, so if there is no question, is there any question? I'm going to move to a different application.
So how do you find these threshold for the soft case? Like, does it depend on the p-value, probability of error?
Yes, that's a good point. It depends on p. So here I have only p and there is no variance. This is what you mean, right? What is the variance? So we fix the variance so that the soft flip probability, the tail, has value p. So the integral of this tail is exactly p.
I see.
So that if we have our soft model and we compute the probability of a hard flip, it's exactly p.
Okay.
And that's designed like that so that we recover the standard phenomenological model if we discard the soft outcome.
Okay.
Can I ask, this error model, it doesn't seem like it has any biasing like I would get from decoherence, where ones decay to zeros during the waiting time as opposed to just Gaussian noise. Am I wrong, or is this just Gaussian noise with none of those kinds of decoherence errors?
That's absolutely correct. There is no decay, there is no bias. Here, everything is symmetrical. It's a model that is realistic in some cases, like if you expect the two states in which you encode your information to have the same energy levels. But we are going to introduce the decay now. So we are going to use a different model where we have a decay from the excited state to the ground state.
There is a question from the seminar room. So what about the optimal soft decoder?
The optimal soft decoder, we don't know. As far as I know, it's an open question. We could try to use some some statistical physics arguments similar to this. It's maybe possible because the math is very similar to the random bond Ising model. We will have continuous spins instead of plus or minus one. So maybe there is some hope to find a crossing point numerically and to get an estimate. We haven't done that. It requires some work.
But so the degrees of freedom are continuous, you're saying? Continuous.
Yes, at least in some of them.
Kind of a weird stat-mech model, I guess.
Yeah, maybe it's a bit weird. An alternative is to try to design a decoder like a tensor network decoder. And if you design an optimal decoder and you can simulate it for large enough sizes, you will get the optimal threshold. I'm not sure which one is easier.
Thanks.
Thank you. Okay, so now I'm going to discuss the measurement time optimization. And I think it's one place where there is a significant gap for improvement of the surface code or any error correction scheme. But before optimizing the measurement time, I need to introduce the measurement time. So I need a model which depend on the measurement time. So we have a qubit. Here in this case, it starts on the state 1, and we turn on our measurement apparatus. It starts integrating some signal, and it gives us something that looks like a random walk with a drift. If the qubit is in the excited state, the random walk is drifting down, as we can see in this example. And when it's in the ground state, it goes up. And based on that, based on this plot, we extract a measurement outcome, a soft measurement outcome, which is going to be some real value, which represents the likelihood that the state was 1 or 0. So this model it seems very clear in this model what's happening. It goes down, then it goes up. In practice, we have a much larger variance or a much shorter measurement time. We don't want to measure for very long to have such a clear picture. And it's also noisy. So we see something that is closer to that, where in these two random walks, it's not very clear what is the direction, what is the trend. So it's not as obvious to extract. In the first case, the state decay, so it slightly goes down and up, but it's not obvious. And in the second case, it's not clear at all that the state remains remain excited the whole time. So in that case, we have a lot of soft information, and this is what we want. We want measurements to be short and to give us enough information, but not too much. Otherwise, measurements are too long and more noise accumulates. And here I'm gonna explain our model as a function of 2 parameters. So we have a probability to decay, which was not present in the previous model, and we have a relaxation time that controls this probability to decay. Let's start first with a very large relaxation time. Then, when we increase the measurement time, I'm going to go down through the last column. When we increase the measurement time, it separates our 2 distribution. We shrink the variance, and we get a more precise measurement outcome. So we want a large measurement time. However, if the measurement time is too large compared to the relaxation time, we are in trouble. And I'm going to go left through the last row. When I reduce the measurement time, we see that the excited state decay towards the ground state, and after some time we start sampling from the state that decayed. So the distribution on the right side start moving towards the left distribution, start moving towards the right distribution, and we get confused. So we want a measurement time that is long enough, but not too long compared to the relaxation time. And we simulated this model for some parameter set and with a few surface codes with 3 different distances. And we compared 2 different things. We compare the optimization of a single measurement, which is obtained by computing the probability that there is a soft flip, assuming the two input state with the same probability. So I give you a uniform qubit, 0 or 1, and we want to minimize the probability of a soft flip. It's a natural model for a single measurement. And instead of that, what we suggest is a global optimization. Instead of optimizing a single measurement, we should optimize the entire error correction scheme with the measurement. And this co-design gives us a better logical error rate. What we want to optimize is the logical error rate. We don't really care if we have bad single qubit measurement as long as we have good logical qubits. And we observe a very, very big gap between the 2 models. If we optimize a single qubit measurement, we get a measurement time that is independent of the code and the distance. And if we look at the distance 19 surface code with soft decoding, it's the bottom green plot here, we get a logical error rate which is close to 10 to the minus 7 instead of 10 to the minus 4 for the single qubit optimization. And we get a measurement time that is about 5 times faster. So we can simultaneously speed up measurements and improve the quality of our logical qubits. It's really doubly beneficial. We have nothing to lose in doing that. And the reason why it works, it may seem magic, but it's actually very intuitive. It's because if you measure for a shorter time, there is less noise on the waiting qubit. And when you measure one ancilla qubit, next to it, there is 4 waiting data qubits. And these 4 waiting qubits accumulate noise. We want to avoid that. So it's better to extract less information, less reliable information, but to wait for a shorter time. Is there any question about this second model? Or about our results?
Yeah, I don't see any questions.
Okay.
Is there so this plot, is that when you optimize numerically over these two quantities, like measurement time versus decay time, or is it easy to find sort of the optimal point for training off like?
Yeah, I see what you mean. So we don't need to optimize decay and measurement time. We assume that we are given a qubit with a decay time, which is part of the system. We cannot change it, and we optimize the measurement time. So what we do in this simulation is that we compute the logical error rate per round for different measurement times. So the horizontal axis is the measurement time, and the vertical axis is the logical error rate. And we see that what we want is a minimum logical error rate. That means the minimum of this plot. Yes, thank you for clarifying. I should have explained what were the 2 axes.
Okay, thanks.
And is it the case that for large distance code, you see larger effect?
Yes, it's true. So we observe, so there is 2 different effects. There is first the gap between hard and soft. And we see that the gap between hard and soft decoder becomes larger, which is great. We have an even bigger improvement for larger code distance. It's natural because the logical error rate will depend on the code distance, and the code distance become larger. So we can expect it as a larger effect. And the second thing we observe is that it's not clear where the minimum is, where's the optimal measurement time here for each plot. And it seems that for the hard plots, it stays in this region. I don't know if it's exactly the same point or if it's going towards the right side.
Yeah.
If the measurement time is, the optimal measurement time is increasing. And for the soft case, it's a bit lower. So the soft information allows you to even speed up further the measurement. We have a speed up already using hard information, but using soft information, it's even more significant.
Mm-hmm. Thanks.
Thank you.
How sensitive is this to the specific type of noise? You took random walk noise, which is kind of a worst case scenario, but if you took like white noise, is it similar?
Yeah, it's so what we expect is that the general behavior, the macroscopic behavior should be the same for most noise model. We expect an improvement. It's very natural because qubits are waiting during the measurement. But the exact value will change depending on your model. And maybe for some model, it's not going to be a factor 1000, it's going to be a factor 10. I don't know exactly which value to expect. It depends on the exact model you pick. And it's going to require some future work to refine the noise model for each specific device.
Yeah, thanks. That makes sense. Thanks a lot.
Thank you. Okay, so now I'm gonna move to the more technical part. I'm gonna try to give you an intuition how these soft decoder work, how they are implemented. and what kind of performance we can prove. We can see the performance numerically, but it will be good to have a decoder that is not only a heuristic, but a decoder for which we can have a provable performance. So here I represent nodes which are the plaquette outcome. It's a different representation. Don't get confused. Nodes are not anymore the qubits. The black nodes are plaquette outcomes, and there is a qubit on each edge. And what we observe when we try to decode is that a Z error on a qubit is detected on the two endpoints. We have a non-trivial outcome, -1 on the two endpoints. And if we have soft outcome, we will have a soft outcome on the nodes. When we have a chain, a path of errors, we detect also the two endpoints of the path. And the goal is to correct this error configuration given the plaquette outcomes only. How do we do that? I'm going to briefly review the hard minimum weight matching decoder, which is from Denis Kitaev-Landal Preskill. And it takes an input for the syndrome nodes, so those nodes with a non-trivial outcome, and it's supposed to find the error that produced those nodes, those non-trivial outcome. The first step is we select these four nodes, these four syndrome nodes, and we compute all the possible distances between pairs of nodes. For instance, the distance between A and C in this graph is 3. So I'm going to put an edge with weight 3 in this distance graph. And once we have done that for all the distances, so there is about n square of them for n red nodes, we compute a minimum matching. We want to find a pair of paths whose total length is minimum and that connect those nodes by pairs. So here we find AC and BD, which minimize that. And based on that, we are gonna connect A and C and B and D by two paths with length 3 and 1, and it gives us a minimum weight correction. It's the minimum number of errors that can explain this syndrome. This is the minimum weight matching decoder. So now I'm gonna add a few details. First, that was in the 2D case, in the case of a perfect measurement. If we don't have perfect measurement, we need to run multiple rounds of measurement. So we run D rounds of measurement for a distance decode. Here we see 3 layers of measurement outcome and 1 final layer. And in this, we now have a 3D graph with horizontal layers representing qubit errors and vertical edges representing measurement flip. And the second thing is that edges will have different weights that correspond to the error probabilities. We will have an error probability on the vertical edge that correspond to the probability PF. So it's about log of PF. And on horizontal edges, if we have a qubit with an error rate PQ, we will have log of PQ. Okay, now, how do we move to soft decoding? We need to add this likelihood, this soft information. So we have this plus or minus 1 on edges. We will put the hard value on vertices, sorry. We will keep the hard value on vertices like we had before. And we have this extra information, the likelihood, that tells us how confident we can be in the outcome. With 0.14, for instance, we cannot be too confident in the outcome plus 1. It could be a flip. So we need to inject this information inside the decoding process. And we do that by changing the weight on vertical edges. The weight on vertical edges is going to be a soft edge, and the weight will be computed by computing the log likelihood ratio for given our two functions f0 and f1. So we get a soft outcome mu. We compute the hard outcome mu hat, and the other hard outcome is mu hat prime. And we compute the ratio of our two functions in this given node, for this given measurement. And the log of the ratio gives us the weight. It's defined in such a way that it corresponds to error probabilities. So we have two types of edges. Some edges on which we have the typical weight, which is given by the fault probability, log of PE, roughly. And some soft vertical edges on which we need to compute a log likelihood ratio each time we get a soft outcome. So some are static, some are dynamic. And now, why did we define the weight in such a way? This definition is designed to guarantee this property that we can recover the probability of a set of faults given the sum of edge weight. So let me try to explain the notation here. We start with a fault set X, which represents a set of fault on some of the qubits and some of the measurement. And we observe a measurement outcome, M, which is the soft outcome. So it's a vector of real values. And what we want to know is what is the probability of a given X? What is the probability of X given M, given the soft outcome? And we want to find the one with maximum probability. What is the most likely error, the most likely set of fault? To do that, we will express the probability of a fault set, the conditional probability of a fault set, as a function of edge weights. So we define the edge weight with this log likelihood ratio to make sure that by summing edge weight, we recover this conditional probability, the log of this conditional probability. And once we have that, we can guarantee that the decoder works. So how do we run the decoder? Before telling you about the performance, to run the decoder, it's almost like the standard minimum weight matching decoder. So the standard minimum weight matching decoder is the hard minimum weight matching decoder is the blue block. And the only thing we need to do is that we need to pre-compute the soft weights. So this soft weight will vary. Each time we have a soft outcome, we need to compute the log likelihood ratio. And there is some additional cost due to some computation that cannot be pre-computation anymore. But the decoder has the same scaling as the hard decoder. Okay. Now I'm going to describe a second decoder, which we use because it's faster. It's significantly faster. We'll see that the scaling goes down from n to the 5 when we use n measurement outcome to almost linear, n alpha of n, where in the sense of the inverse Ackermann function. So we use this decoder because it's faster, and it's the union fine decoder that we introduced with Naomi Nickerson a few years ago. And I'm going to describe very quickly the union fine decoder, and then I'm going to tell you what is the difference with the soft union fine decoder. And finally, we are going to discuss the performance, the theoretical performance. So first, the basic idea of the union fine decoder is to avoid to compute all these distances between all the pairs of nodes. When you have n red nodes, you will have n square distances to compute, and it costs a lot of time. It's too expensive. So to avoid that, we are not going to compute distances. We are going to use the fact that if there is a red node, we know that there is a neighboring error. We know that one of the four incident qubits must contain an error. So I'm going to grow a cluster incident to a red node, and I keep growing around these clusters until they meet. When they meet, I can check if I can match them together. I know that there is an even number of vertices inside this red cluster that just merged. So I can implement a matching inside. I will be able to match them. So I will stop growing this cluster. It's a valid cluster from now. It can be corrected. So I will stop there. And I'm going to keep growing the other clusters. And they keep growing of a half edge. And at some point they meet. Again, I have an even number of syndrome bits. I can match them and correct this cluster. So I'm going to stop there. Now I have two clusters to correct. I can correct them independently. And it's easier to correct a single cluster. We can do it in linear time instead of correcting the entire graph. So that's the basic idea of the union find decoder. To move to soft information, so first let me tell you why it's called union find. It's because to track these clusters in linear time or in almost linear time, to update them and to track which vertex belong to which cluster, we design a variant of a union find data structure. It's based on union find data structure. So we call it union find decoder. And to move to the soft decoding, we need to grow a weighted graph instead of growing of a half edge everywhere, growing uniformly. This is similar to the work of Human and Brown. So after modifying the union find decoder, we obtain a soft union find decoder. And the main difference is that we optimize a little bit the gross, but we need to take into account the soft weight. So similarly to the minimum weight matching, the main difference is that we need to compute those soft weight dynamically, which is which has almost no cost. And there is no pre-computation, no change in the pre-computation. So in the end, we obtain a soft union find decoder whose complexity is almost linear instead of m to the 5 for the minimum weight matching for m measurements. And I'm going to conclude with what we can prove about these two decoders. First, we can prove using the key lemma that I mentioned before, that since error probability correspond to edge weight, we can guarantee that the minimum weight matching decoder and the soft minimum weight matching decoder return a most likely fault set, even for soft information. And the second thing is that for the soft union find decoder, we do not have this property. It does not return a most likely fault set. However, we see that numerically it performs well. It gives a very close approximation of the minimum weight matching. And we can guarantee that it corrects any fault set if the weight of the fault set, so sum of the weight of the edges, is small enough. Is smaller than some weighted minimum distance over 2, which is a generalization of the hard case. Okay. So to conclude, we can benefit from soft information, and we get a significant improvement in the performance. It works for any kind of distribution, as long as the distributions are independent over different qubits, different measurement outcomes, and different time steps. We can do the exact same study with higher dimensional Gaussian, which are maybe more realistic in practice, or with a Poisson distribution, or any kind of distribution that you think is relevant for your device. And there is a significant improvement due to hardware-software co-design. By designing together the measurement and the quantum error correction scheme, we can get simultaneously faster measurement and better logical qubit. And I want to point out also some work in with continuous variable with Gottesman, Kitaev, Preskill encoding. And in this case, it's very natural to consider soft information, to consider some kind of analog information, because your measurement outcome is naturally a continuous variable. And there was some design of some variant of the soft minimum weight matching for this specific device and this noise model. Thank you.
Thank you for a very interesting talk.